And, but I'll hand over tonight to our speaker. Katla Satya.
Yeah. Thank you. Good evening, everyone. I'm Satya. I'm a PhD student at the University of Southampton. Working on the future of wireless communications. Am I audible? Am I audible enough? Am I audible?
Yes.
Yeah.
Louder.
A bit louder?
Please.
Yeah. Okay. So I'm a PhD student at the University of Southampton. I'm working on the next generation mobile phones. That's my area of research expertise. So today we'll discuss about the 5G, the next generation technology. So before that, I'll take you on a journey to this fascinating technology from pigeon-post to holographic phone calls. So holographic, as you can see on the slide here, there's a hologram where I can participate in a conference in Hyderabad, which is the place I come from, and I can simultaneously give a talk in Southampton here using my hologram. So this is the future of next generation mobile phones. So I'll take you from pigeon-post, how the evolution of the mobile phones from pigeon-post, where pigeons were used as message carriers. So before that, I just want to ask you a couple of questions. What's the first thing that you do in the morning with your gooey eyes?
Water.
Wash your hands. And what's the next thing, last thing you do at night with your bleary eyes? I think these questions are not appropriate to this generation. These questions are misplaced. It's not right for this venue. But what we usually do is this. So we basically keep pummeling your mobile phones with your limp, light, and flimsy fingers in the morning and at night. So a day doesn't pass without this device. And so this is what we do, and this is a wrongly put slide here. So, but how much? Mobile phones has become a ubiquitous means of socializing, text, paging, and now internet everywhere. But how much do we know about this mobile phone, this device that you held in your hands every second? Do you know what's happening in your mobile phones?
Magic.
So what is that magic? So this is the skeleton of a typical mobile phone. You have these are the block sets that are embedded deep inside your mobile phones, which you can't see them because they are covered by a slim and sleeky cover case on your case, so you can't see them. If you open them, you'll see each and every block of this. So I'll not get into the details of each and every block, but as we go on, I'll basically unbox every box and I'll tell you what's happening in each box. I'll not go into details though. So typically this is a source, which means that when you talk on your phone, this serves as an input. So your message signal is the source, and then it's basically you just for the time being, just let's ignore this channel encoder and the source encoder, and then you have a modulator where, for example, in the pigeon-post, what is it that carries your message? It's a pigeon, right? You have a message or an envelope. You enclose your message in the envelope and give it to train a pigeon, so it carries over to the your friend or colleague or family, anyone. So here the modulator, this is basically the pigeon. So you have a source which is your message generated by your vocal cords, and then you modulate the signal, and then you have an antenna which is like this. This is pointer. You have an antenna. It can be a copper. It can be anything. So and then you just transmit over the channel. This channel can be either air, water, copper, or fiber. So these are the medium for transmission. So if it's air, it's wireless communications. If it's water, it's acoustic underwater communications. If it's copper, it's a landline communications, and fiber is an optical communications. So depending on the medium, hence it has the name wireless or wired communication. So and then the message signal that has been transmitted will be received by another antenna on the second party, and then it basically does decoding, and which I'll discuss later, and then you receive the earpiece of your mobile phone. So this is basically the basic functioning of a mobile phone. And there's a vast body of research happening on these two boxes and these boxes. So I'll take you now on the evolution of wireless communication. So this is a pigeon-post, this is the modulator we have now. And so wireless communication started with, well, much before pigeon-post, we have the smoke signals, where the smoke were used as as a message. People gathered around this message. Basically, the smoke serves as a signal. So when this smoke billows from a wood or something, people gather together and they communicate basically. That's as a carrier. Now, I do not want to go back further, so I just started with pigeon-post, where pigeon is used as the message carrier, and then came telegraph, which is a wide communication, and then we have mobile landline, and then we have first generation mobile phones, and then we have text, voice, video calls, which we do on 2G, 3G phones, and then the future is this. Right now we are here. This is the past, this is the present, and this is the future. So let's see how. Well, let's see the enclosed details of the evolution of cellular technology. So this is the first generation SIP technology. G stands for tech generation. We are now using 4G, and the next year you will see 5G in 2020. So what is 1G, 2G, 3G, 4G? Any idea? Probably you must be knowing this 1G. This is an analog signal, being, you generate the signal. So, okay, do you remember this block diagram? So, in 1G, you don't have this, you don't have this. You only have source, modulator, and just transmit. So, it's like you generate your message signal, your voice, and it's directly modulated using a carrier, and then fed to the antennas. You don't have these two in 1G. So that's the difference. Did you ever see this bulky phone?
Yeah.
Did you see this? But I haven't seen this.
Only in central London, I think.
Yeah, it's in the museum now. So this is the first generation. So we have only voices. So voice is the only thing we can transmit. Nothing else. No text. Nothing. It's analog, which means that it's not digital, as in analog in the sense whatever I'm talking is analog. So 2G is more digital communications, where 1G is analog communications. I'll tell you the difference between 1G analog and digital. So this is your message signal. Let's say assume that it follows this undulating, nice, smooth undulating waveform. And this is the carrier, this is a pigeon. So basically this message signal needs to be carried by this wave, which is called carrier wave, for the name carrier. So we multiply this with this. Like you see the pigeon carrying its envelope in its beak. This carries on this amplitude. So the amplitude is this one. So it gets affected here. So because of this signal, so it's called amplitude modulation. This is analog communication design, and it's very susceptible to human blockages. It's not a very robust system. And then we have FM radio. So it's frequency modulation, where so if you guys observe here, the amplitude, the frequency is unaltered. I mean, it's the same. It's only the amplitude is altered. It's changed. Because the change in the amplitude is basically the signal. If you see this this change in the crust and trough here. So that's basically this is signal. Whereas in FM, you will have the frequency change. The signal is modulated in the frequency. So this frequency keeps changing. So that's FM. Maybe FM is also obsolete now. So in 2G, 3G and 4G, so this is 1G. In 2G, 3G and 4G we have digital communications where the signal, let's say this, you have message signal, it is discretized, which means that it's sampled. You take one sample, instead of having all the message signal, you just take one sample of the message signal. One sample, when you sample them, if you insist of having a whole continuous signal, you can discretize discrete set of points which are represented as bits. So you sample it here, like this is like 0, and this is like 0 or 1, and it can be 0, 1, some sequence. You code them. So this is basically digital communications. Why do we need digital communications? Is analog communication not enough?
I think with digital, it's easier for computers.
Easy to?
It's easier for computers to work out.
No. That's. But where is the computer involved in it? Yes, please.
The quality doesn't be great.
Yeah, exactly. Yeah.
But you can store it in different media.
Right. Yeah. That's right. Yeah. So the quality, you can use the spectrum more efficiently, and it's more robust to blockages and everything. It's more quality of service is very high. This is because of these two blocks. They chip in 2G. In 1G we do not have, but this is this remains. These two blocks remains in 2G, 3G, 4G, and any other and the next generation communications. So these blocks ensure that the signal is more robust to blockages and blockages and the fading because the channel is basically this one, and it is not constant. It keeps changing with time. So this encoder, source encoder and channel encoder, they basically encrypt your information. So even when there is a blockage, even if it suffers a blockage, you have a decoder, source decoder, which can decipher the signal, basically the encrypted signal. It can decipher more accurately than the analog communications where you do not have these two blocks. So this is for this channel encoder, which means that this corresponds to this air, water. Depending on that, you have its own channel encoder, and source encoder is encrypting your message signals which is being generated by your vocal cords. So that's the difference between 1G and the rest of the communications. So, but what is the difference between 2G, 3G and 4G? Anyone? No? Okay.
Data rate?
Sorry?
Data rate?
Yes. Data rate is higher in 3G than 2G, and 4G is higher than 3G. Do you know why? The value is the same. Let's say 2G, 3G is assuming they are the same. Bandwidth is the issue, but let's say they are the same bandwidth. In 2G, basically the transmission, the mode of transmission is different. Let's say this is carried out in TDMA fashion, like time division multiple access, or in frequency division multiple access, which means that let's say you want to, let's say I want to talk to you. Like this, I have two groups now. If I want to talk to you, one group, group A and group B, I need to allot particular set of time. As in, let's say I have time 5 minutes. I need to talk to these two groups. I cannot do simultaneously. I can just apportion these time slot into 2.5 minutes and 2.5 minutes. So there is a loss in the data rate. That means I can talk to you only for 2.5 minutes. And 2.5 minutes to say. I cannot give my entire 5 minutes to you. Right, so it's like I'm dividing the time. Because if I do not divide, I cannot, so there's an overlap. So let's say you want to talk to me, and I want to talk to them, so it is not possible. Either I can hear or I can talk. I cannot do both. So it's like I'm dividing the time. So in this process, there's a delay, and because of this, you lost the information, which I could have sent if I have the rest of the 2.5 minutes. So this is a time division multiplexing. You have frequency division multiplexing, where you have a range of spectrum, like frequencies, and you allot frequencies to each group. I allot, let's say I have two frequencies, F1 and F2. Frequency is basically, you know what is frequency? The frequency is this, let's say, so this signal, the number of cycles per second is basically the frequency. So it has, when you have, this is the time domain. When you take in the frequency, you have basically the set of each frequency is basically the number of cycles per second. Anyway, so if I divide the frequency, the given frequency, let's say I have F1 plus F2, and if I divide the frequency into two groups, I'm losing the information again, because I would have more rate if I communicate with you in both channels, F1 and F2. But I'm losing here when I'm dividing. So the 2G is basically operated on TDMA and FDMA. So a 3G is a CDMA, which is basically called code division multiple access. In which means that I give a unique code to you and unique code to you. They both do not overlap with each other. I mean, in the sense that there is no interference between the two codes. So I can simultaneously, transmit, or I can simultaneously talk to two groups with my using unique non-overlapping codes. So in the same, I have the same whole time slot of 5 minutes, and I'm using both frequencies F1 and F2, but I'm using different codes. There's an encryption being done. This is called CDM, spread spectrum. This is derived from the, as you were alluding
Many of them are.
Yeah.
Hollywood actors.
Yeah. So this is called spread spectrum. There are two spread spectrum techniques. One is the this is called the direct sequence spread spectrum, and the other one is frequency hopping. This is code division multiplexing, and the other is the frequency hopping spread spectrum. So I have basically it's an encryption. So there is no overlap between two groups, and I can use the whole time T1 and T2 and F1 and F2 simultaneously. Hence, I have high data rates here. What is 4G? So now you understood what is 2G, what is 3G. So in 4G, you have something called orthogonal frequency division multiplexing. So you have a what is it? I mean, here in 3G, not entire spectrum is used, but there is a limited spectrum. And there you have CDMA. Here you have a lot of bandwidth, and it's wide band, which means eventually you can run more. You can send more data, right? More data, and you divide the entire bandwidth into chunks of frequencies. They are called subcarriers, and you can, and they are basically orthogonal, again, like code division, like CDMA, where the codes are orthogonal. Here the frequency is orthogonal, and you have a wide band. So you can transmit more amount of data, and there are not only this, but there are other techniques like carrier aggregation and some other more sophisticated algorithms which make this 4G more faster than 3G, 2G, 1G. So this is like this. You have 2.4 kilobits, 64, 2000, and then 100,000. So it's much faster because of the way it is being transmitted. But they are all digital except the 1G. So right now we are here. But do we need 5G? So now we are moving to 5G. Do we need 5G? Is it 4G not enough for us? So why do we need 5G? Because of this. So there is an exponential. So this shows this is a bar chart. It shows the data rate, the data consumption between 2017 and 2007 and 2017 and 2023. 2003. 23, sorry. 2023. It's an expectation. So there is an exponential growth between these 2 years. Am I right in saying that there is an exponential growth here? No, this can be linear as well. I do not have one more point to say that there is an exponential growth. It could be linear. I can just join these two. Exponential should be something like this. Like this, right? I need at least one more point to support my argument that this is exponential. But I do not have one, but just believe me that this is an exponential growth. So, to meet these data rates, we need 5G. And what is 5G? So what is a 5G going to do? What are the, how is it going to meet the challenges, and what is it going to solve for us? So 5G is basically trying to enhance the mobile broadband, which means when you in your mobile phones, right now you have 4G. Have you ever seen when you surf YouTube video, it keeps buffering? It's not very what's it? It's thick. And whenever if you observe that, for example, it happens to me in Waterloo, I don't even get a dial tone sometimes. You know, it keeps engaged. It's unengaged. You don't get a dial tone. That means the spectrum is occupied by people. So the data rate demand is high. So you need to enhance the mobile broadband, and it also aims to address ultra reliable low latency communications. It means that the communication is reliable, ultra reliable, and low latency. It's very quick. Why do we need that? I'll just tell you on my subsequent slides. And then it's a mass-machine type communications. So communication between two devices. And we have Internet of Things. Do you know what is Internet of Things? Internet of Things is where every device is connected to every other device. For example, let's say you have your mobile phone, which mobile phone or some device strapped on your wrist. It measures your blood pressure or heartbeat or sugar levels, and then it can report to your GP. So GP can immediately check your data, your levels in blood sugar, blood pressure, everything, and he can directly give you an appointment, or he can give you a piece of advice. So without your knowledge, it just goes to it relays your information, all information from your mobile phone or from any other device from you to GP. So that's like one example of the Internet of Things. And you can operate, let's say you're struggling to turn off the light there. You can actually do that with your mobile phone. This is connected to that, and you can turn it off. So every device is connected to every other device through Internet. So for that you need lots of bandwidth. And 4G is not going to solve that. 3G it didn't. So 5G, does it solve it? We don't know. Let's leave to the future. But that's what we aim for, as in to address some of these issues. So who is? I mentioned that ultra reliable low latency communication. I'll talk about this meanwhile. But who is this surgeon? Do you know this guy? And what is he doing here? Any guesses?
Oh, it's the Italian,
Sorry?
the Italian inventor character.
Italian inventor, who? Marconi?
Earlier, the Renaissance. Another. Called Da Vinci.
Da Vinci, no, he's a painter, and he's a painter, he's everything's a polymath. but he's not any radio engineer. But what's happening here? What is these two? What are these? Who is this guy? Have you seen him in news or anywhere? And what is this guy doing here with this scribbling on his notes? He is scribbling something, and there's something happening here as well. Is he a surgeon? He doesn't have any scalpel or anything in his hands. He's just operating. He's in a room where you have all the medical instruments, devices, and then he seems to be relaxed, sitting on a chair, scribbling and scribbling on notes. Is he a surgeon? Any ideas? You can see this one. This. What is happening here? This is the future. That's the reason why I'm asking. I'm stressed. Something is happening between this and this. He's doing wireless surgery. This is a guy in a spaceship. So this surgeon is basically, and by the way, who is the surgeon? It is a speaker himself. It's myself, it's me. It's me. This is me. But this is not me. This is a patient in spaceship. So this guy and I are operating using a robot controller. So these have robots. He's in a spaceship which is very expensive and is in space somewhere, near Mars or somewhere, or the moon. He's hovering there, and he had some problem with his body, and he cannot find a doctor there. So there he has basically informed me before going to space, or after reaching there, he informed me about this is a joke, okay? Don't take it seriously. Okay. So he informed me to operate on him as a surgeon. I'm a PhD student. He doesn't know the difference between a doctorate in wireless communication and the doctor. So he informed me. And I'm trying to go into the. I went to the general hospital and scribbling. I took the notes, which is an e-device, electronic device, and has all controls of the robot here. I made him lay on the table here on the what's that? Yeah, operating table. Yeah, and then these are the robots, robotic arms. They're not human arms. They're robotic arms. And they're basically jaded into his body and jarred into his body. And I'm operating these robotic arms wirelessly using my controller here. It could be anything. It's like a notebook here, but it could be like joysticks playing around, like child playing children playing joysticks on the computer. I'm playing with these joysticks on him. So for this you need ultra reliable and low latency communication, because this is so sensitive, so there's a personal life at stake here, and you need to have a reliable communication, and it should be so quick. It cannot have latency. It should be low latency. So 5G is going to be the 5G and beyond. This is the next future of surgery, and this is This makes more sense when there is no doctor in the remote areas, or like I said, in the spaceship, or in a remote area village where there is no doctor, and the doctor in the urban area, or like in the city like London or in New York, he can operate on a patient who is far away, who doesn't have access to proper infrastructure or something, but he has robotic arms, okay? But he doesn't have anything else. So that this is where one of the examples of where you need ultra reliable low latency communications. What else does future has in store for 5G? So 5G, so this is a low latency. So 5, you can watch the sports from the athlete's point of view in a 3D, in a 3D view, using this. You can have ultra high definition 3D live video of sport events from athletic points of view. So you have some sensors here which is broadcasting what's happening right in front of him. So you can watch through his lens. using a 5G and beyond equipped device. And you can stream high-speed videos in a high-speed train. Right now, I don't even get proper video without buffer. So, but you can get a high-definition video in high-speed train using 5G. And using 5G, let's say there is some accident or something, it's a natural calamity or something, and there's an air ambulance is going and hovering around the area of the calamity. And in this scenario, energy is more important, as in you do not have the supply, the battery consumption is very crucial. So it should consume less energy while operating. Let's say these guys are operating on a patient here. This is an air ambulance, and they're operating on a patient. In this case, the energy consumption is a crucial. So the 5G should be able to consume as much less energy as possible and produce very good results. Okay? And here, this is another example of low latency communication, where this guy is operating the drones, these are unmanned aerial vehicles, to kill pesticides, to kill pests, to kill the microorganisms on the field, on the grains. So basically, this is a 5G aided agriculture. So we can do agriculture with 5G. So that's what we have. It's so exciting and so wonderful. But is it really as fascinating as it looks? Is it as bright and hunky-dory? Or is it just a myth? Or did we just open a Pandora's box? Is it full of problems, or is it full of exciting news? Let's look into this. Why is it a problem? Why did they mention that it's a Pandora's box? Is because our goal is so high that we need to have enhanced mobile broadband, low latency communications, and machine to machine, as in every device talking to every other device. But is it really possible? That's a question that we need to ask. This because, let's imagine that there are two taps which are filling the water bucket, and the access to the water is from the hole at the bottom here. So there is no other way you can access to this water except from the hole at the bottom. And let's say if you have two more taps filling it, what will happen? It will just overflow. You miss the water. You cannot collect this water. This being spilled over, it's overflowing from the bucket. So you do not have access to the water. You cannot access it. So what do? Anyone? Yeah.
Have a larger pipe.
Yeah, increase a larger one. It's just simple. You just increase the size of the hole. Now it looks good. You can have more and more devices, and you can access it. But how much more you can go? How much can you increase? So this hole in wireless connection is called bandwidth, and this water is called information. And these tabs are basically your mobile phone, laptop, washing machine, laptop, cooker, everything. It could be anything. So as I said, if your mobile phone has to communicate to your GP, it should not, because it's so important. There's a vital information is being transmitted to your GP. It's about your medical situation. It should not get lost in the traffic. It is more important than a friend transmitting a video or a funny joke or something. So it should not get lost. It's a more important, crucial information, and it's being lost because there is no bandwidth. So we can increase the bandwidth, but there is only limited bandwidth. We do not have as much as we want because it's given by the nature. Bandwidth is basically the set of frequencies. F1, F2, I said F1 plus F2. So we have a range of frequencies, but we do not have unlimited bandwidth, unlimited frequencies. So how do we go and solve this? How do we circumvent this problem? So there are 5 magic bullets for the future wireless communications, wireless technology. These are, it's called massive MIMO, millimeter waves, beamforming, full-duplex, and small cells. What is MIMO? It's basically multi-input, multiple output. You have multiple input. Let's say you have, do you know how many antennas does this phone have? This phone has?
2.
Yeah. So this has 2 and the laptops may have 4. So that's basically MIMO. That's because you have multiple input. If my mobile phone is connected into your mobile phone, which has 2 antennas, and have 2 antennas on my phone, so it's like a MIMO. I have multiple input, multiple output, which I'm transmitting, and you have multiple input, which is signal is coming, incoming signal is it's being received by the antennas and the receiver. So it's called multiple input, multiple output. So massive is basically you have a large number of antennas. That's called massive MIMO. If you can have several hundred antennas on this, the whole wireless communication will be different. I'll tell you why. And millimeter wave films. So this is my terrain. This is where my PhD lies in. This is my expertise. And beamforming is also my terrain. And full-duplex is basically, this is my fringes of my terrain where I borrow I use some concepts from millimeter waves and apply on full-duplex. And massive MIMO, why I call it the sharecropper is because in sharecropper what you do, you rent the land and give the crop as a rent. So massive MIMO is basically you have multiple antennas, not a large number of antennas, where I borrow them from massive MIMO and I use them here in millimeter waves. This is why I call it the sharecropper. It's sharing antennas to me to achieve beamforming gains. Beamforming gain is usually done by large number of antennas. And small cell is basically the range where how far you can cover the signal basically. Let's say there is a term base station here. Have you ever seen a base station? Do you know what is a base station?
One just behind it.
Yeah, okay. So you know what's a base station? It's like it's a cellular. It's a must where you have something like, I don't have a finger now, but you have rectangular kind of blocks of antennas, four antennas basically, and they communicate with your they transmit signal basically using those antennas. Those are antennas basically. So how far can it reach? How far it can transmit? The coverage area is called a cell. And it's better to have small cells than having large cells. It's because in your small cell, you can have multiple base stations. So you can continuously talk to many base stations. Like let's say there are 20 people here now. If I have one base station and I'm talking to 20 people, is it this better, or let's say I have one base station for every single person here? Which is better? I dedicate a base station to you, to one individual. So this is better because you have whole access to the base station. So if you have more, it's like you have a base station and it covers an area. Let's say it covers this 1 kilometer range of area, and if I decrease it, if I reduce it to 500 meters or 250 meters, for every 250 meters I have more base stations. That means your data, the quality of service will basically enhance because I'm I'm dedicating a whole base station to you, and the base station will talk to another base station. So that's a different story. So you have more small cells. Full-duplex. What is full-duplex? Full-duplex is basically I'm talking to you, and I am also receiving from someone. So can you talk and listen at the same time? Can you?
Politicians do. They like to kill us, they do.
Right. That's nice one. Yeah, Lucian. Yeah. So apart from politicians, who can do this? So no one can do this. So transmit and receive at the same time. So that's basically full duplex. So what's the benefit of full duplex? So what happens typically in mobile communications is that whether it's 1G, 2G, 3G or 4G, 5G or 10G, so the communications happen two ways. Like I have F1 and F2, let's say two frequencies. I use one for transmitting, I use F2 for receiving. These F1 and F2 are orthogonal, so they do not interfere with each other, and I can successfully transmit without any interference causing to the received signal, and I can listen properly, I can decode without any error in the message, because they're being transmitted and received on different frequencies. So that's what's happening. So what is full duplex? In full duplex, you transmit and receive the same frequency in the same time. So I don't need F1 and F2. I just need F1 or F2. I don't need both. So I'm basically utilizing these frequencies more efficiently, which means that it doubles the spectrum, nearly doubles the spectrum. I'm able to transmit and receive. So increasing the data rate twice when I have half duplex, where transmission is on one frequency and reception is on one frequency. So that's the point of full duplex. So the idea of full duplex is to increase the spectral efficiency, which means to double the data rate. So full duplex serves that purpose. Beamforming is basically where you see the beam, but I'll come to that later. So now I'll focus on millimeter waves, this is my area. So what is a millimeter wave? There's a typo here. This is not 100 meters, it's 100 millimeters. So what is a millimeter wave? So right now the 4G is operating here. We are here now in the 4G. So this 3 gigahertz, roughly somewhere here, 2.4 gigahertz, 2.4, 2.41. So we are here in this area. So this is sub 6 gigahertz. This is not millimeter wave. Millimeter wave gets its name from its wavelength. Wavelength is on the order of millimeters. Do you know what is a wavelength? Oh yeah.
The distance between two consecutive.
Yeah, right. That's right. This wavelength. So this wavelength is a function of frequency. So, right, frequency is equal. Wavelength is velocity of the speed of light divided by the frequency. That gives you the wavelength. So typically, if you observe the base station on the backside of this hall, and the spacing between the antennas will be half the wavelength. Let's say you have two antennas. Even in this mobile phone, you have two antennas. So they are separated by a distance of half wavelength. Wavelength of that frequency. The mobile phone is operating at 2.4 gigahertz. So half the wavelength, so velocity of light is like 3 into 10 power 8 divided by 2.4 into 10 power 9. So that gives the wavelength. So half the wavelength is the spacing between the antennas. So which means typically the order will be in 100 millimeters. Now millimeter waves basically starting. So there are two advantages here. One is because of the spacing, because of the wavelength is reducing, wavelength is decreasing. There's an advantage for that. And there's another advantage as we move to higher frequencies. But what is that advantage?
You have like more chance for data to be.
Yeah, why is that?
Because the swap.
What? Swatch. I didn't get it.
High frequency
Yeah.
means that the waves will. It's like.
Right. You're close.
Yeah.
Yeah. So it's basically you have more bandwidth. As I said, you can, let's say you have 300 megahertz here, 3 gigahertz. So the gap between this, so this is basically bandwidth, 300 and 3 gigahertz. The bandwidth is basically the difference between two frequencies called bandwidth. Let's say this is F2 and this is F1. So F2 minus F1 is the bandwidth. And the bandwidth here is 3 gigahertz minus 300 megahertz. It's roughly 2.7 gigahertz. Right? Yeah, roughly 2.7 gigahertz. But if you see here, let's say this 30 gigahertz and 300 gigahertz, you subtract this 30 from 300, it's roughly 270 gigahertz. This is 2.7, this is 270. Like 100 times more. So you have a lot of bandwidth, which means that you have more frequencies. I can transmit my information on 270 frequencies. Let's say each division is one frequency, as in 331, each one is 1 gigahertz. So I have 270 here, whereas I have 2.7, like 2 or hardly 3. So I can transmit lots of data on this. And the other thing is, spacing between the wavelength is so small. The spacing between the antennas, which is a function of wavelength, which is basically a function of wavelength, will be reduced now. It will be small. So I can accommodate on my mobile phone or laptop a few hundreds of antennas. So why do we need antennas? I'll tell you in just a moment. But although we have lots of bandwidth, so a lot of frequencies, it has challenges. The thing is, it is more susceptible to blockages, attenuation because of oxygen, rain, and here in England it rains all the time. So because of that, the signal gets attenuated. So the signal, in the sense that the energy of the signal that's being received on your phone will be very, signal energy will be very low. So you cannot decode the signal more successfully because you don't have enough energy. Let's say if I speak low, if I lower my voice, if I tone down my voice, can you hear me? You can't. Because the energy, in the per rate, the energy that's being received by me, by you is less, because the power I'm generating to talk is very less. So, in order for you to hear, I need to increase my voice. This kind of energy. So, but here, let's say there's a wall between two of us. Although I'm raising my voice, if there is a wall or something, then the wall basically attenuates the signal. When in another room, the next room, or on the outside, he cannot hear me because there's an attenuation because of the glass doors and walls, ceiling, and tube lights. There's a metal here. So each one causes attenuation, and they also reflect. Metal reflects the signal, so it bounces back to me again. So I cannot successfully receive the signal. And there's a foliage attenuation because of let's say I have a signal here. You can see the energy of the signal fades out as it progresses through the trees here. So this is strong here, and it gets weaker and weaker as by the time it reaches the third tree. So it is more susceptible to blockages, unlike the frequencies in the unlike the frequencies here. These are not susceptible. They can reach long distance even though there are blockages, but not these frequencies. But we want this because there's a lot of bandwidth here. We don't want to waste it. So what do we do? And it's also more susceptible to blockages. Human blockages. If I hold my phone if I hold my phone like this, I may not receive the signal. If I hold like this, I may receive. And so it depends on the human blockages as well. So let's see. These two is a transmitter which is being transmitted on a millimeter wave, you can see here these 2 points. This block. The signal is blocked here, while it is reflected, diffracted, and reflected here. These two. So, but it doesn't happen in 4G. So how do we increase the received signal power for successful transmission? Any ideas? Just tell me one simple idea, as in that strikes your mind. How do we increase the signal power? Well, let's say if I want to talk to you and you're not hearing me, what should I do?
Shut it off.
I need to raise my voice. Yeah, increase the amplifier. You know, I need to eat lots. Or oh, I forgot my hot chocolate here. I should drink this. To increase the signal power. So if I want to raise my voice, I need some power. So I can just increase the signal power of the transmitter, the base station. Right? One of them is to increase the transmitter power of the base station. But we cannot do for many reasons, for 2 reasons. One is we have limited power, and the other is you cannot keep increasing. Although if I keep increasing my voice, I have a parched throat and I cannot speak tomorrow morning. So I may become dumb. But what happens with the communications here? So there is a limit on how much power you can increase. You can, although if you have infinite amount of power, let's say even if you gather all the power in the world, muster all the power in the world, and you pump it to transmit a signal, but it's not advisable because it causes cancer. Do you know why? It may cause cancer because the electromagnetic, it will microwave your brain, you microwave your body. It's because of the energy. It's basically, these are electromagnetic radiations. So the radiations has its own energy, which when increased beyond limits, it can ionize your cells in the body, which are cancerous, which are carcinogenic. So that's not helpful. So you cannot go on increasing the limited the transmit power. So what can we do now? So we have limited power anyway, but even if we have infinite power, you cannot do that because there is a Telecommunications Union which has put a ban on the limit. So there is a threshold for the maximum power you can transmit. So one way is to increase the power without having any external source is doing directional transmission. So ideally, so 4G, this is what's happening. You have omnidirectional transmission. So where the signal energy is all pervading, which means it is spread in all directions. I can receive my signal there, here, everywhere. You cannot see it with your naked eye, but if you have a filter which can see the electromagnetic radiations, you will see it everywhere. But so if the user, if I am here and the base station is here, it can transmit to me. But why is it transmitting here? It's a wastage of energy, isn't it? It's transmitting in the directions, undesired directions. So maybe if I collect all this energy and point it out only this, I mean, so let's say I have, let's say this is P, transfer power, and this is P, this P1 and P2 is the rest of the transfer power, and I can use the same P2 I can steal the same P2 power to this user. So then I would have P1 plus P2, which means that this entire wasted energy is basically is being used at this user, right? So I need to steer this entire, this undesired, the wasted signal into the desired direction. So I can amplify the signal without being involvement of any, without being in the involvement of any external source. So this is called beamforming. So did you see the 5 magic bullets? One of the magic bullets is the beamforming. If you remember, it's down the millimeter waves. So this is called beamforming. So This is the beamforming, the magic bullet there. So how can you do beamforming? Have you seen these antennas before? In the rooftop. These are called Yagiula antennas, and these are parabolic antennas. So these are direction antennas. So you have multiple, each element here is called an antenna, and you have multiple metal stripes here. So these are called antennas, and they achieve beamforming to steer the beam in a desired direction. If you twist the antenna array in a different direction, you may not receive the signal because the signal is being directed in one way and you are trying to receive the signal in another direction. So you can't do that. So parabolic antenna is one such directional antenna, and Yagiura is one such antenna. So this is the next 5G and maybe 6G going to be. So you have antennas. So you have several antennas here, a few hundred of antennas, because as I mentioned, the wavelength is on the typical wavelength is typically in the order of millimeters. So you can have several hundreds of antennas here, and using these antennas, you can do beamforming, where you steer the beam. Beamforming is possible only with large number of antennas. If you want to narrow beams, where the signal wasted signal energies, if you want to minimize the signal wastage, you need to have more and more number of antennas. So you have like a laser beam like a signal. So it's like pointed signal. So these is a 2D, basically this is arranged in 2D fashion. So you can have control over elevation and azimuthal. This is called azimuthal, the XY plane, and this is Z. So this is called elevation angle. So with 2D arrays, you can have 3-dimensional control. That's the reason for having a 2D panel here. And these are several antennas. So beamforming is possible only with a large number of antenna arrays. So there is no, you see that the yellow, blue, pink. What is color? See,
Green.
Huh?
Green.
Is it green?
Yeah.
Okay. Not kind of green. It looks here. Yeah. So there is no interference between these, 4 users, and it is a pointed beam. So it's not wasted in any other direction. So the signal energy is amplified by using pointed beams.
The same frequency, the yellow, the red, and
The same
the
frequency.
same frequency, but
Same
different
frequency,
directions.
exactly.
Right,
The
okay.
same frequency. So the interference, yeah, this is one advantage. It's a good point. So the advantage is that there is no interference as well here. So they are using the same frequency, same time. There is no CDMA here. It's not like 3G code division. So there is no concept of code here. So it's the same frequency, same time, but it's not full duplex. It's only transmitting. It's not receiving. It's not full duplex. So it's transmitting same frequency. So the leak, there is no leak. There will be minimum leakage. It cannot be without interference, because if you want to have without interference, then you need to have pointed beams, which means that you need to have large, like few hundreds, thousands of antennas. So you can have more laser-like, pencil-like beam. Then there will be no interference. It's hardly possible. So there will be leakage, but not much. And people can, multiple users can use the same channel, so same frequency in same time to communicate. So that is the advantage. So this is an example of how beamforming can be achieved. So these are antennas. These are antennas. Let's say you have 8 antennas here, and these are phase shifters, which means that they steer the beam in the desired direction. Instead of having in all directions, transmitting in all directions, this theta 1, it's theta 1, theta 2, theta 8, this ensure that the beam is steered in one particular direction. So the more the phase shifters I have, the better resolution, the better beams I have. So these are used. You cannot see them on your mobile phone or on the base station, but the background in the back of the antennas, this is what happening. So they try to steer the beam in particular direction to get a pointed beam kind of thing, something. So we want to get as narrow as possible. This is thick, but we want as narrow as possible. And this is another full-duplex communication. So as I said, so this is radio 1 and radio 2. It's transmitting. The red one is the transmitter signal, and the blue one is the received signal. So it's transmitting and receiving. You see that the red line attenuates as it progresses through the channel, and the green line, so the blue line also fades as it progresses through the space. So this is because of the path loss, because of the distance. Because the guy here can hear me louder than the guy at the back, because there's a loss in the signal. It's the same thing. So you can hear this guy is hearing. You can have, but it's not possible to humans in here. So you can hear and receive at the same time. You already have enough confusion. So this is under, if you remember, the passive mind I was talking about. So this is one array, a circular array of antennas, which provide beamforming, and you have two more here. It tries to give you the diversity, in the sense that let's say I'm talking to you, and my speech is not only, it's not pointed. It's transmitting. It's being going in all directions. So there is a reflection from the metal. There is a direct line of sight, and and there are many other reflections, right? So if the signal may be blocked, let's say if someone comes here in between two of us, and you can still hear me because there's another signal coming from the reflection from the wall. So there is a diversity. So if you have both my line of sight signal and the reflected signal, then you can make a better judgment about the information that I'm transmitting. If you have the worst case, if one of the paths is blocked, you still have access to another path. So that basically improves the fidelity of the signal. So this is the reason why we have multiple antennas. So you can there's a transmission from this antenna. There's a transmission from this antenna array and from this antenna array. So basically, it doesn't happen individually. They all the signal, there's some processing happening back side of these antennas, where they collectively transmit, and the signal will be received from this may transmit something like this, and this may transmit like this, and this may transmit from another path. The same user. So you have three paths. Let's say that you have three paths, the same user. So you can decode. You will have basically when you collect these three signals, you will have more signal power or more robust reception, because you can make a judgment based on the three signals. You have more information now. So you can, let's say you have some fake news being going around, and you don't know what's the fake news. So basically you, three more people, let's say there are 4 people, and 3 people say the same thing, and one guy says something else. So you make a judgment based on the probability, right? So the probability that it is, these 3 guys saying the same thing is high, then the probability that, the probability that the statement heard from these 3 guys is more truthful than the probability you heard, property of the message being truthful from the fourth guy. Because three guys same thing. Three guys say the same thing. So you have better knowledge of this than the fourth guy saying some false news. So if all the four guys say the same thing, then well, you know the truth. But three guys, the probability is little reduced. Is decreased, but you still can make a better judgment. So in the same way, you have 3-4 paths, multiple paths by having an array of antennas. So there are multiple paths. You can receive signal from multiple paths and make a better judgment on the signal. If one is blocked, that means it's saying false information, and you can rely on the other two. So that's the point of having massive MIMO, which is called diversity. You are listening to the information from various sources, diverse sources. So that increases the fidelity of the information. So what have we learned this evening now?
Clever stuff.
Yeah, what's that? I will be happy to hear what have you learned, to know what you have learned this evening. So I took you to the next generation communications from the pigeon-post. From pigeon-post, where pigeons were used. So have you got any questions?
Where are we at with this? Because
Sorry?
where are we actually at with this? Because I've heard of deployments in Korea. Is that correct?
Correct.
5G. It sounds as though it's very much a work in progress, or is this the established technology that is being deployed, or is this an embellishment on what's already been deployed? Or?
No, it's not already deployed yet. I mean, commercially it's not yet.
Right.
There's work happening. There's work under progress. But so basically, there's an organization body called ITU, International Telecommunications Union.
Yeah.
So they put basically all the companies like Samsung, Ericsson, and other telecommunications big companies. They bring up the ideas and they put forward, they propose the ITU, and ITU basically
Establishes
it's
standards.
basically commercial. It's a compromise between companies. It's more in the commercial than the technology. So then they start making the product. So the ITU has scheduled the 5G by the end of 2020, roughly 2020. So next year there are already there's no commercial deployment yet. The trials have been going on. Like this is Qualcomm in the US, and Samsung in Korea, and there are some other companies as well. So, but no one is sure if the 5G works.
Mm-hmm.
Because the millimeter waves that I mentioned now, it is not in the 5G now, as in, because there are many challenges technically. I mean, it's easy to give hours and hours of talk, but technically, the electronic components, they cannot cope with the millimeter wave high frequencies, ultra high frequencies. So the 5G, what we do now, what we hear about now, it will be massive MIMO and the beamforming, but not the millimeter wave. Millimeter wave may be 6G or something, or 5.5G. So it's like 3G never served the purpose what it's supposed to do. 4G, there was 3.5G and then 4G. So 4G didn't do what 4G has to. So 5G will never do what 5G is supposed to do. So it's just the anticipation, the hype. So next year, hopefully, you'll see. I'll finish my PhD now, and then you'll see the 5G handset next year.
So a 5G handset would have those multiple directional beamforming arrays built in.
Yeah.
So I'm assuming that everyone's mobile phone built in would have an updated regularly a database of where all base stations are and where the X, Y, and Z coordinates are. So when you make an initial hookup, that's beamformed in the direction that's expecting a base station.
Yeah.
in the very first instance. Is that
Exactly. So the initial access happens to 4G, the LTE, the long-term evolution. So because the beamforming, for beamforming to happen, it needs to know the angles of departure and angle of arrival. So it's not if it's line of sight, like if it knows the coordinates, like you're there, I'm here. If I know it's a line of sight, I can just direct the beam to you. But let's say there are multiple blockages here. There's no line of sight here, and so it can depart from in this angle, and it arrive at your antenna in different angle. So there is no clear understanding of the angle of departure and angle of arrival. So what initial access, so basically the initial communication happens using LTE. Why? Because LTE is omnidirectional. So I transmit in all directions. So I know where you are and what is the channel, what are the blockages, everything. So basically learns them and then implement the do beamforming. So this is initial access. Initial access using
and is the term phase array exactly the same as beamforming? Or
yeah, phase array.
The two terms for exactly the same
Right,
structure.
It's how you do beamforming. Yes.
And the early days of satellite TV, there was things the public called squareals. Was that the same technology? Instead of parabolic dishes or...
Yeah, the satellite communication is directional, yeah.
That was the same structure inside those square panels? Or?
Yes, everything is already there. We are reinventing the wheel, basically. So the satellite is a line of sight. There is no obstacle, nothing. It's easy. Parabolic antennas, there's a high gain antennas, directivity. So the beamforming has been there since ages. The 4G, the OFDM, the orthogonal frequency division multiplexing, which I call, was there like in late 1940s or something. But it happened. It materialized only in 2004 or 7 or something, roughly. That's because lack of hardware. Did not have the electronic chips that can make 4G happen. So even 5G, the phase shifters, so to steal the beam, you need to have phase shifters, which the hardware is now currently lacking. So, and beamforming is there ages ago. Yeah. So just reinventing the wheel.
In your eyes, what's the future hold?
Huh?
What does the future hold?
What does the future hold?
Yeah.
In my eyes.
Have you hologrammed yourself from India to here?
By
any means whatsoever.
I would hope to make a holographic phone call for my wife, for defense. I'll be in India and having my defense here. PhD. So,
is there much sort of to change to 5G? What would be the sort of infrastructure cost? I'd assume you'd have to change at what level? Whether it's satellites, individual transmitters, where I'd assume it would be a big infrastructure, or you said it was already there. So to implement, assuming you can get it all going, what's the infrastructure for this?
With millimeter waves, it's completely different infrastructure. But with other things, it looks similar. As in, it's not much change in terms of infrastructure.
Right.
But I'm not very sure about this. But to the best of my knowledge, with excluding millimeter waves, it should be the same as the current standards, the infrastructure. Because if it takes a lot of time, then I don't think it can be reality so soon.
Yeah.
Because if you need to rebuild the infrastructure and everything. So,
can you see 5G being pervasive, or is it likely to just augment 4G? For example, you'd have a 4G backbone that you would augment it with 5G in the areas where it warrants it.
Because we can have back compatibility.
Yeah.
If 5G is not available somewhere here, then I switch back to 4G. Yeah, and like 4G now does, when you don't have 4G, it goes back to 3G, 2G.
Because I imagine that sheet of paper would block 300 gigahertz. Just that sheet of paper would block 300 gigahertz, wouldn't it?
It depends on the material of the paper. So, but it can block, because it can block the human. Human can block. My fingernails can block. So it depends on the material as well, the properties. For example, metal reflects the signal wood blocks the signal, buildings block the signal.
What about severe mist fog conditions in the atmosphere? Would that block?
Yeah, there's attenuation. Right? So
Yeah,
the 60
right.
gigahertz, yeah, for example, the 60 gigahertz,
Mm.
here, the blockage is so high. So this cannot be used in cellular communications.
Right.
So though we have high, all possible varieties of frequencies here in millimeter wave, we cannot use all of them because the attenuation is high in these two, for example. So this is only possible for indoor. You have 60 gigahertz Wi-Fi. IEEE is called Samsung has launched this, as far as I'm aware. So you cannot use it for outdoor communications, but for indoor, yes.
Any more questions? Any more questions?